came up with this. All these would be in food. And so to come up with these, we originally said, let's push on this frame with 100 kips of load. And then we said, okay, I've got 100 kips of lateral load. I can then look at the translational stiffness of each of my columns, because these are going to be what's contributing to the lateral stiffness of my frame. And I can distribute this 100 kips based on the ratio of stiffnesses between each of these columns. Then what we did is we came up with fixed end moments based on the translation of this 100 kips up here to these columns. And what we found out is when you let the joints rotate in this and you do moment distribution, you actually relax that 100 kips to be a smaller value. Because when we distributed it to these two columns, we were just looking at the translational stiffness of the frame by itself. So when we relax this frame, we get a lesser amount of force. And what we ended up with was an applied force up here of 73.63 kips. So we originally said we were applying 100, but when we account for the flexibility of the frame and the fact that these joints have rotational capacity, they're not infinitely rigid rotationally, we end up with an actual applied force of 73.63 kips, which generates these end moments. And so every time we looked at, let's say, a scale factor on this, all we were doing was we're scaling this force from 73.63 up to something, right? So when we did our first no sway analysis of this frame, we had an imbalance of force of like 81 kips here on the first frame. So we scaled this from 73 up to 81 and then added these moments to the frame that we had with the no sway case, so we had equilibrium again. And so all that we did was take 81 over this as a ratio, and we scaled up these moments as well. We did the same thing when we wanted to get, let's say, the unit push of 100 kips. Yes, we originally said we were applying 100 kips, but if we're using these moments, like this, we're ending up with a lateral force of 73 kips. So if we want the unit moment, you want to scale all these moments by a factor of 100 over 73.63. So then you multiply all these end moments, and that's what we saw if we did look at our table, where we said the unit moment column, right? So we had the unit moment column, and then we had the hinge number. I think this is where we lots of questions. You had hinge A, B, and C. You saw unit moment of 1228, 974, 798. This is just 588 times 100 over 73.63. This is just 717 times 100. And this is just 904. I wasn't doing anything special or magical here. I'm just scaling those up based on the work we've already done. Because once you have a certain value here and you get the moments distributed like this, you can scale this to whatever you want. You can just scale the moments along with it. So if you applied 100 kips of load here and you got your moments back out from the actual 100 kips of load, you'd find that the moments would be 1228 here, they'd be 974 here, and they'd be 798 there. So that's all I would do for that, yes?
Just want to clarify. The reason that that happens, that there's not 100 kips there, is because it's free to sway?
No, because the joints have rotational capacity. When we're distributing originally, we're saying, look at the stiffness, the translational stiffness of this column, the translational stiffness of this column, and then we're distributing the force solely based on that. But what happens is, as you do that, and this frame moves over from that lateral force, you get rotation in these joints, right? So you have to account for that rotation. And what's happening is when these rotate, they actually reduce the amount of force you thought you were originally applying. If you had infinitely rigid joints here, where there's no rotational capacity there, then you would just distribute the force down here and you're done. Right? But the fact we actually have rotational capacity of these joints, they're not infinitely stiff rotationally, means you have some moments that get distributed, and you have to account for that. But the scale factor is, yeah, maybe that wasn't too clear. You're just taking this lateral push, and rather than doing this every single time you want a new lateral force push for this configuration, once you do it once, you can just scale this up and down to whatever values you need. That's all we're doing there.
Scale it up and down, varying for what?
Depending on what lateral force you're interested in.
So is 100 kips just arbitrary?
Yes.
Okay.
Right? You can do 0.0152 kips if you like. 100 kips is just nice because it's a unit load, so to speak, that's easily scalable. Right? If you have a scale factor of 17.86 like we did, then that unit force of 100 kips is really nice. You just multiply 100 times 17.86, you easily get your total force to form your first hinge of 1786 kips. Okay, it's just numerically easy that way. But yeah, you can use whatever unit you want. Yeah.
And looking at how we did the same thing last week with 81.3, you don't have to reset it to 73.63. Say you modify, say you scale it to 100, and then later on you want to scale it to 147. You can then just go 147 over 100.
Yes, absolutely. As long as you're using then these values associated with that 100 kips. Yes, it just scales up and down directly. Yep. So we left off last time where we just formed our first hinge, and we had found out that joint A, we said this was A, B, C, and D, and we have hinges at the tops and the bottoms of the columns, like so. We found out from our analysis that our first hinge is going to form at A. And what does this mean? Well, we had a moment rotation curve for these guys that look like this. Where we have no rotation of this joint whatsoever, meaning it's fixed, but then suddenly we hit the plastic moment, which is what we're scaling everything for. We're going to look at our capacities of this section, and we looked at basically the moments in each of these joints, and we wanted to find out when did one of these joints hit its critical capacity or hit its plastic moment. And so we found then that joint A hit its plastic moment, which means now it's at this location. Instead of accumulating more moment in that joint, instead of increasing moment, we're just going to start rotating. So we now have rotation of this joint, which means it's going to behave like a pin. Right? So even though this pin still is carrying a plastic moment of whatever we found it had, 25,000 kip feet or whatnot, it's now just going to rotate freely instead of accumulating more moment. So we can treat it like a pin, and instead of accumulating more moment at that joint, we just leave it at the plastic moment of MP, and we do our analysis henceforth as if it's just a pin. So that's what we're going to be doing then, is instead of having this fixed now, you now have this joint A behaving like a pin, and we can redo the analysis. And so what we're interested in then is applying a lateral load of 100 kips again. So we're going to do the same process, yes?
We know that the hinge is forming at A because it has the largest unit moment of 1228 up there? Or
No.
how do you know that it's the...
Remember that we did a table
Yes.
on the very end of class last time? So we came up with this big table. We looked at each hinge. We looked at the moment capacity of each of those.
Yeah.
We then looked at the demand on each of those. And we then looked at how much moment capacity is remaining based off the demand and the capacity. And then we looked at that unit moment, and we said how much additional force laterally is required in order to form a hinge at one of these joints. And we found that at 1786 kips of lateral force on this frame, we formed a hinge at A. That meant the plastic moment in joint A was equal to, in this case, 20,000 kip feet. That's what that table was doing. Yes?
Are we gonna finish this table?
We'll keep expanding that table as we go, yes. So we have two different tables going. We have one that looks at hinges and it looks at the plastic moments, each of those hinges, and then we have another one that was looking at the frame as a whole, looking at the displacement and force capacities of the frame. So we had two different tables there. But we determined A by looking at the plastic moment capacity of each of the joints. We looked at how much demand was on each of them, and then we said, okay, now I want to keep pushing on it laterally, and how much force is required in order to form the next hinge. And that's how we came up with the scale factors, and the smallest scale factor indicates which hinge will form first. And so we determined just from that table that the hinge will form at A. So now we're going to move on to the next step of the analysis, but we're going to change A now to behave like a pin. So even though it's not a true pin, for the purpose of our analysis, it has no more moment capacity, so we can treat it as a pin. So as we're increasing our lateral load now, it doesn't really matter what this has done beforehand. It's fixed at that moment capacity. So if we look then, members A, B, and C, D, look at our translational stiffness. So the translational stiffness of a fixed pin system is 3EI over L cubed. You'll note that member AB, before when this was fixed, its translational stiffness was 12EI over L cubed. So now its stiffness is decreased. And this makes sense. As we're getting plastic behavior in our structure, we're getting softening of the structure. So the total translational stiffness of the frame now is lower once this hinge is formed. And so we expect to see then, as we keep pushing this frame over and new hinges form, we'll get slowly more and more reduction of translational stiffness of the frame, which means the whole thing is softening. So we originally have a very stiff system when it's elastic, but as nonlinear behavior starts to occur, we start getting inelastic behavior, and therefore the stiffnesses start decreasing. I didn't sum these up, but if you want to get your R factors, if you look at the ratio of this stiffness to the total of the two, you find out this distribution factor is 0.4. For member CD, if you look at this individual stiffness versus the sum of the two, you get a factor of 0.6, and once again they sum to 1. So you should always do this check to make sure you're summing back to 1. That's a good way to check for any calculation mistakes you can potentially make when you're looking at E's and I's and all that sort of stuff. So what this tells us is I have 100 kips applied here. So member AB has a distribution factor of 0.4, which means it will take 40 kips of this load. And this guy will take 60 kips. And we will get end moments now forming at the tops of the columns. You'll note now for member AB, we no longer have this inflection point in the middle as we did before. Right? The deflected shape for this guy is now like this on both of them. So there's no inflection point with the deflected shape here, which means moment at BA is just 40 kips times 30 feet. (1,200 kip feet). the moment it's CIV, moment at the top there. 60 kips times 30 feet. Or 1,800 kip feet. So the same process now applies. We want to do moment distribution because this analysis is once again assuming that we have complete fixity of these joints from rotation. The reality is they don't have complete fixity, so we have to let these moments distribute. And so we want to do moment distribution. So the idea is to come up with new distribution factors based on the rotational stiffnesses. So same idea. Rotational stiffness for a fixed pin would be 3 EI over L. For a fixed, it would be 4 EI over L. And once again, we look at joints B and C. I look at the adjacent members. So essentially the same thing applies as before, but the only real difference now is member BA, instead of being a fixed, is now a fixed pin. You can see every time we have a nonlinear event now, and every time a hinge forms, we have to reassess all these distribution factors. The translational stiffness of the frame changes, as do the rotational stiffnesses of some of the joints. to refresh, or moment distribution now. I'm doing the simultaneous joint release. You can also release joints one at a time if you prefer. But when I'm releasing this joint, I'm taking this 1200, I'm applying an equal and opposite moment to the full joint, but multiplying this out of balance moment by the distribution factors. So 1/3 of this 1200 will go to the column side, and 2/3 will go to the beam side. Same with this 1800, I apply an equal and opposite moment to the full joint, with 3/7 of this going to the column, and 4/7 going to the beam. I'm underlining to indicate that everything above that underline is in equilibrium, but because I released these joints simultaneously, I didn't account for the fact that when you distribute this here, 1/2 of this will go to the other side, because when you have a fixed connection, 1/2 of the moment will transfer to the other side. You're just including the flexible deformations. So I generally draw the arrows here. And now this joint is out of balance 515 kip feet, and this joint is out of balance 400. And we'll rinse and repeat. What you will notice, I'm not taking anything over to the side now. We did before because this used to be a fixed connection, but now because it's reached its plastic moment capacity, we can't distribute anything over here because it has no more capacity. So there's nothing distributed to joint A. Once again, I went farther than this in my notes, down to ±1 of imbalance, but I'll abridge it here just for the sake of clarity.
What would you recommend on the homework?
I just like going to usually ±1, but usually you just pick amount of tolerance that's reasonable. So most of the time people say within 99%.
Okay.
It's good, but again, that's up to your judgment.
Okay.
You can automate moment distribution to be done with a computer program if you like, and then you may as well go as far as you need, right? There's no difference in going, say, 10 steps versus 50 steps in terms of your computation time. So generally the idea is you want to see these two being equal and opposite, which is what they should be from equilibrium. So if you stopped, let's say, up here, these two wouldn't be equal and opposite. But again, as long as they're within, let's say, 1% of each other, you're good. You'll see for this one right here. Those are off by 1 kip foot, 1 rounded. Once again, I'm interested in the actual amount of lateral force applied to this frame now. We originally said it was 100 kips, but we did not account for the flexibility of the joints B and C. And now that we have accounted for that flexibility, that applied load will be lower. And we can reason out what that is based on these end moments. some simple statics. We know, just by looking at one of these beams, this shear force, Vd, is just equal to this moment divided by the height of the column. In this case, the height of our column is 30 feet. Our moment is 1136 kip feet. 1136 over 30 feet yields 37.87 kips. Same thing for this guy. 948 over 30 is going to give us our shear force V of A. We just sum these two together, because they're both in the same direction here. We get what the actual lateral force applied is associated with these end moments. 69.47 kips. And because we're interested in a unit moment of 100 kips, because that's what we're going to be scaling for everything, we just scale this up using a factor of 1.440. So we take each of these moments and multiply by 1.440 for everything we're using for a movement, or for a unit moment. So that's exactly what we'll do next. We're now interested in seeing which joint forms a hinge next, because we still have two plastic hinges left in our frame system. Right? Joints B and C, the tops of those columns, both can form a plastic hinge.